All right, so let's go ahead and get started. Appreciate everybody's interest in Credo. So Credo is well, first of all, my name is Bill Brennan. I'm the CEO of Credo. And for those that aren't familiar, Credo is a pure play, high-speed connectivity company. We build solutions first for the Ethernet market, and then we'll be moving to other standards as they go much, much faster. So the data center has been great because it has been the facilitator for higher speed. So the need for speed and the need for higher bandwidth has never been more exponentially increasing. The opportunity, we think, in breaking bandwidth barriers boils down to the SerDes, which is what we do very well. It's the core of all of our connectivity solutions. And when you want to understand the future and the bandwidth barriers and how to break them, it's all about the SerDes. It's all about going faster. It's all about going wider. It's all about doing it with better energy efficiency. All of the presentations that I attended today, we talk about green, we talk about sustainable, energy efficient. So I might use some of those words today too. So if you look at the core of what we do, all of our connectivity solutions leverage our SerDes expertise. We have an application-specific mindset as it relates to our designs. That means that we optimize for a given speed, a given reach, a given protocol. And what you get with that is energy efficiency. It's a big miss, we think, in the rest of the industry to do a universal one-size-fits-all sledgehammer. And so that's how we've built our success over the last really 10 years plus. So I guess, I spoke about Ethernet. This is really the first market that we entered. And the reason is because there's an exponentially increasing speed curve. 10 years ago, it was 10 gigabits per second. We quickly went through 25 gigabits per second. This is single lane data rates to 50 gigabits per second. 100 gigabits per second is in production right now, and we're working on 224. We'll enter other markets like PCIe as the speeds move towards 64 gig with PAM modulation. The degree of difficulty with that design will enable us to bring the same kind of advantages to that market that we've brought to Ethernet. I guess one final note is we're one of the fastest growing chip companies in the market, and we have the distinction of being the only big tech IPO of the year. And so definitely could not have predicted that in January when we went public. But now I get to show this, safe harbor disclosure. So I'll do a little bit more on Credo before I get into what we see in the future. So Credo is unique in a sense that we address every Ethernet connection in the data center, all of the copper links as well as the optical links. Probably most notably, we've been the pioneer for a new multi-billion-dollar market, which we refer to as active electrical cables, or AECs. We enable very innovative server rack designs, as well as we enable disaggregation at a switching and routing layer. We also build optical DSPs, line card PHYs, and we've kind of quietly become the SerDes chiplet leader. I guess the best example of that is the partnership with Tesla that was announced a few months ago. We were their connectivity partner as they developed their Dojo supercomputer, not only licensing them our IP, but also building SerDes chiplets that are now in production. As we look at one other thing that we do very well, we license our IP to companies that are doing devices that we're not planning on building. You can probably guess when energy efficiency is of high priority, we're typically the choice. And so when we think about the network in the data center, we typically think about what's happening above the server, basically from the NIC to the TOR to the leaf spine and the tier 3 router. But more and more, what we see as we begin to look into the future, that there's an exponentially exploding network within the server itself. I'm not known for saying controversial things, and I could say that Moore's law is dead, Dennard scaling is over. That's not controversial because I think everybody at this conference has talked about it. What this means is basically that the cost per gate curve has been increasing since 28 nanometer. That was a process that was released 10 years ago. And as we move towards 5 and 3 and 2, we actually see an acceleration. So what does this mean? This means that architects need to completely rethink how things are done. And so moving to higher utilization workloads, moving from the enterprise all the way to SaaS, moving towards disaggregated processing. Many people have talked about that today. The one-size-fits-all x86 is really moving towards accelerators, whether they be GPUs, DPUs, TPUs. Even the locations are being distributed, from a central data center to the edge. And what is the impact of all this disaggregation? From our perspective, it means increasing bandwidth, and it means the need for faster SerDes with wider buses. So let's look a little bit deeper into the server. So we'll talk about the 2020 era server first. Pretty straightforward, traditional. A couple of x86 CPUs moving data between memory storage and the NIC, which communicates to the outside world. When you dissect it from a SerDes perspective and a total bandwidth perspective, we've got 80 lanes of 8 gigabits per second, or PCIe 3. That creates an internal bandwidth to the server of about 640 gigabits per second. As we look to 2025, when we see the effects of disaggregation, we can track that, that architecture to be, core CPUs. They might be ARM, they might be other specialized CPUs that really become a hub or an I/O controller, a supervisor for the accelerators. We see that the speeds and the lanes, there will be a tremendous move towards wider, and there'll be a tremendous move towards faster. So we see Gen 3 moving to Gen 6. That's an 8x increase in speed. We see lane count going from 80 to 400. That's 5x in speed. In addition, we'll see the need for UCIe chiplets. As these different designs are going towards max reticle, a common thing will be to push the SerDes off chip. The UCIe chiplets will drive these PCIe lines, and we also believe that we'll see retimers to move all of this data around the server. This doesn't come for free, though. When you look at it from a power perspective, this is a big challenge. So if we go 2020 era server, we look at the power consumed by the SerDes alone. It's basically 1% of the kilowatt budget that's popular for a server. As we look towards 2025, big issue. When you go 8x faster, 5x wide, that's a 40% increase. That's a 40x increase in total bandwidth. And if we look at kind of a traditional universal SerDes in 5 nanometer, 64 gig PCIe Gen 6, we think that the total power consumption of the SerDes will go over 400 watts. So this is a big challenge, and it kind of leads to the idea of application specific. So let me first talk about universal, what I like to call the sledgehammer SerDes. Basically covers a wide range of speeds, a wide range of reaches, and a wide range of protocols. It's like an x86. I guess it's analogous in the sense that it supports everything, but it's optimized for nothing. Our approach is the application-specific approach, where we pick a given rate, a given reach, a given protocol, and we optimize for energy efficiency. You also have some benefit on size going this way, but really, the opportunity here is that maybe analogous to a GPU, this is optimized for one thing. The opportunity is saving up to half the power. So I can call this green, I can call this sustainable, I can call this energy efficient. Actually, I think it's compelling more than anything, because I think the designs in the future, power is gonna go top of mind for sure. So if we dive in a little bit deeper and we look generationally on how we get to this 2025 server, the term picojoules per bit is a common metric on measuring power for a SerDes. You can see that over the progression, we're doubling the speed every generation from 8 to 16 to 32 to 64. And generally speaking, the goal, the worst case goal is to end up at the same picojoules per bit if you double the speed, which means your power doubles. going from 8 to 16. Typically, to achieve that, what we've seen is that the designers need to move down a node in process. And so you see a progression from 12 to 7 to 5. And I've shown the 64 gig example 2 different ways. 420 watts, if you stay in 5 nanometer, you can get it down to a little under 300 watts if you stay in 5. With the application-specific approach, we're confident saying that we'll deliver solutions that are less than 250 watts, even going down to potentially half. We think this is compelling, and we think that this design approach is definitely going to happen in the future for those few players that are able to negotiate the speed curve. So that's a look at inside the box or inside the server. Let's take a look at outside the server. So again, this is going down a path of faster and wider. The graph here is single lane speeds. Going back to 2014, 10 gigabits per second was the fastest IEEE standard that had been ratified. And you can see there's an exponential curve. That's the curve we've ridden to build our company, because this curve represents degree of difficulty, an increasing degree that filters the number of teams that can manage and negotiate this curve. So there's a very clear path towards going faster, and there's also have been historically a very clear path to go wider. SFP was a single lane, 2 directions. QSFP went to 4 lanes. OSFP and QSFP DD, 8 lanes. So when we talk about what's coming next, we've got to be thinking about faster and wider. But in this case, for 224, we believe that it's a hard climb. And I think the industry is starting to figure this out. If we look at progressing from 10 to 25 to 50 to 100, if you double the speed, the picojoule per bit increases by 50% if you stay in the same process node. So naturally, you go down one process, and you can achieve parity with picojoules per bit. Now, it's important to note that typically when you're transmitting over a wire and receiving, we call it a TX-RX pair, 20% of the power is consumed by the TX, 80 is consumed by the RX, because you're doing a lot of equalization, a lot of DSP signal processing. But as you go to 224, that ratio changes. 224, or 112 gigabaud, is right at the edge of the process. So when you're looking at the gain versus bandwidth trade-off, and you say you want to go twice as fast on that transmitter, it means that you're looking at 4 to 6x the power. And so we see that ratio going to 50-50 at the 224 node, which means going down one generation is not going to cut it. So we see it being an N+2, so moving down 2 generations to get to parity. So what does that mean at a high level? 112 gig is mainstream in 5 nanometer. For Credo, with our application-specific design, it's mainstream at 12 nanometer. For 224, we think that parity comes at 2 nanometer for the industry at large, and for us, it's 3 nanometer. So with that being a hard climb, it means it's not going to come soon. But the world needs it. The next higher bandwidth, they need it sooner. So let's talk about wider. So OSFP XD, extra dense, was introduced by Andy Bechtolsheim at OFC 18 months ago. 100 companies have bought into the effort and have been working diligently on this. This goes from 8 lanes to 16 lanes. Lane speed of 112 gig per lane, achieving the next generation port, 1.6 terabit per second port. So I'm super happy to be able to tell you that today we announced, drum roll? I was just having trouble with the clicker. We announced the industry's first OSFP XD device, which I had one of these, and I will have one soon to hold up. But in any case, it is transmitting data, 1.6 terabits per second. It's 16 lanes of 100. It's a standard AUI interface. It's 20 watts per cable end. Thank you. This is it. Small, lightweight. Can you believe it? The 20 watts, so the spec is 40. And so when we talk about AECs, we talk about half the power, half the cost. Our first generation cable is at half the power of what you'll see optical solutions. These are 6.8 millimeter jackets. How thin is that? It's like 2 Cat6 cables. How fast is 1.6T? It's a full-length 4K movie in a tenth of a second. Even more exciting is that this chip, 12 nanometer, it's real time right now. I can start shipping these cables. And so we're super happy. What does this mean physically? Last year, in working with our partners, UfiSpace and DriveNets, we collaborated to deliver the world's largest router, 350 terabits per second, using Jericho 2C+, total power consumption of 57 kilowatts for the 3-rack deployment. The fabric was 400 gig AEC, so 8 lanes, 50 gig, 3 racks. So in the last 12 months, we've gone faster and we've gone wider. With this 1.6 terabit per second cable, and I've never done this before, this is an unveiling. It's kind of fun, right? So what did we achieve physically? The same router, 350 terabits per second, Jericho 3, 25% more energy efficient, and everybody that talks to a data center operator knows that floor space is probably the most critical commodity that they've got. So basically a 67% savings in floor space. Pretty impressive, very proud of the team. We did this in conjunction with UfiSpace and DriveNets, and BizLink is here today. They're the manufacturers of these cables. So thank you. So in summary, I've got the shot clock at 8 minutes, so I've been talking fast. In summary, when we look at breaking bandwidth barriers, it's all about faster SerDes, wider buses with better energy efficiency, which is the application-specific design approach that our team takes. Inside the server, the end of everything from Moore to Denard, that's not controversial. We see disaggregation happening with compute. That'll drive exponential bandwidth, which means the end of universal SerDes as we see it. Outside the server, 112 gigs, the last easy climb. So 224 is going to be harder, more expensive. The solution is to go wider with this OSFP XD. So I really appreciate the interest. I will say that these lights, it's hard for me to tell if people are looking at me or if they're looking at the purple cables. I wanted to tell you a funny story about the purple cables. Why are they purple? Everybody asks me. They're purple because, look, I'm not the quickest guy, but I'm pretty quick if I get hit on the head 5 times. I don't do that anymore. So I would go in to the customer with my black copper cable, even though it was like an AOC, but better, half the power, half the cost, IEEE spec, 10 times as reliable, way more rugged. You're not going to break my cable if you route it like this. And so I got frustrated. Everybody thinks this is a DAC. Hey, how fast is your DAC? How much does your DAC cost? It's not a DAC. So I went to Wikipedia. I looked up AOCs because you can't find a black AOC. They're multicolored. They're all the pretty colors. Not a purple one. So I brought it back to the team and I said, look, we're going to build purple cables. They said, you're nuts. It's the dumbest thing we've ever heard. The suppliers, BizLink, was what are you talking about? Copper comes in black. So I came back the next day and I said, all right, we had a vote. We're going to build purple cables. And they said, we didn't even vote. I said, the vote was 1-0. And that's not my style. But I'm happy that we did that. We're getting great feedback because we're in high volume now. We've talked publicly about the relationship that we've got with Microsoft, very important customer of ours, and the fact that we enabled a very innovative dual TOR architecture. So appreciate your attention, and if there's questions, please let me know. No heckling. There's a lot of guys in blue shirts that will take care of you if you heckle. Chris Cole.
Thanks, Bill. Actually, I'm a huge fan of your insight that passive copper is dead and that these monster SerDes are in the past. So we've just started an effort in the IEEE to actually write a spec. We're calling it medium loss, or we could call it sensible loss. But certainly I invite everyone who kind of has a vision that this monster, fit-all solution is in the past to join us in that effort, because as you know, standards are quite important. So I totally share your vision.
Yeah, we will absolutely cooperate with you. And for those of you that don't know Chris Cole, he's been an exceptional force within our industry. Very active with the standards body. I've been with the company 9 years. I'm brand new to this market 9 years ago. And I reminded Chris of, I talk about him all the time. I was at the point where I didn't have any contacts, so I was cold emailing anybody that I could find with 50 gig SerDes and a name and an email. So I emailed him and said, look, I've got a 50 gig NRZ SerDes. Would you be interested in testing it? And he says, you have that? And I said, yeah. Do you want to test it? He says, no. But can you be in San Diego next week? There's an IEEE meeting, and we want you to present, because it was a big NRZ versus PAM4 modulation argument that was happening. And I've never been to an IEEE meeting. I haven't been since, by the way. It was fun, but not that fun, Chris. And so I told our VP of architecture, who was the only other employee with me at the time, I said, great news, you get to present at IEEE. And it was an absolute chaotic show. There was 20 people on each microphone, some people congratulating, some people saying we were really stupid, but Chris was the catalyst. Any other questions? Well, I appreciate your interest. And if there's any customers that want to talk afterwards, we're open for business. Thanks.